Hi everyone. I can imagine that for most organic chemistry professors, this part of the course it gets to be really exciting because, well, A, we're continually learning new reactions, and B, we're going to learn how to string together 3, 4, 5, maybe 10 reactions to convert very inexpensive starter material into functional molecules. Those molecules could be bioactive. For instance, they could be drug inhibitors. They could act as dyes in like contrast agents when you have a X-ray or MRI. In terms of materials, people can design molecules that can absorb sun rays and convert that into electricity, or make molecules that fluoresce under certain conditions. So this represents, particularly this video, represents our first look into a very important but also substantial synthesis, because going from an alkane to an alkene to an alkyne is 4 reactions, not including a proton transfer. So why don't we look for updates? Why now? Okay. I'm going to show you just right away. There's no need to delay. If we have an alkane, we can make that into an alkyl halide. And how do we make that into an alkyl halide? Br2 and light. And I'm not going to worry about stereochemistry, but in terms of regiochemistry, the Br has to go, in this case, on a secondary carbon, which is more likely than a primary, because we're basing this off of the stability of a radical intermediate. And we knew that. We've seen this before. The radical unit. And then in the elimination unit, we can add a strong base, NaOET, and we're going to get an alkene. Now with synthesis, what you're doing is, in the reaction where you get mixtures, you are carrying forward the major product. Okay, so if you know your elimination unit very well, you know that this would give us a mixture of alkenes. An efficient synthesis carries the major product forward. So let me write that down. Actually, that's actually something we should keep in mind. An efficient synthesis carries forward This is important because when you design your synthesis for an exam, hopefully the problem is designed in such a way that you would never have to carry forward the minor. That would be an inefficient synthesis, right? If you have to purify the minor product and carry that one forward, you want to carry forward the major product. And okay, so far these 2 reactions we know about. We know about this next reaction, though we didn't at the time probably think it was going to be that important to make the halide. And this is where you want to add, or typically add, a chlorinated solvent. Remember this one from the alkene addition unit? Yeah, that. Man, I'm going to try to state which units these are from. The radical unit, this was unit 6. This was the elimination, that was the previous unit, unit 8. and the alkene addition reaction was unit 5. Okay. You see the I don't know, some people think the difficulty with organic synthesis, but some people think it's the beauty, is that now these reactions in different units are all playing together and working together to get us a final product. Our final product is an alkyne. So our alkyne is going to be accomplished by doing a new reaction, and we're going to use NaNH2. Okay. I'm going to put in parentheses, assume excess, unless otherwise stated. And you'll see why in just a bit. Assume excess, unless otherwise stated. Okay. You know, we're not going to put coefficients. We're not really, in organic chemistry, balancing reactions. That comes more so in lab, where you have to do stoichiometry, like you learned in general chemistry. This is where we get the alkyne. And this is a new reaction. Okay. Some of you may be able to predict what is happening here, but this is new. New reaction. And it's our first reaction in Unit 9. Okay. Using NaNH2. This is called sodium amide. Don't ask me why it's called an amide. I actually don't know. Most of you know amides as a molecule with a CO double bond next to a nitrogen. Okay. Don't worry about that. The name of this is sodium amide. And let's label our highway. We went from an alkane to an alkene. Did you notice that to go from the city of Alkane to the city of Alkene, we had to go through a city of alkyl halide? To go from alkene to alkyne, we had to go through a city of dihalide. Okay. Don't worry, I'll explain this reaction, but this is a synthesis. 1, 2, 3, 4 reaction synthesis. I mentioned that there might be a proton transfer. That's going to happen when we're trying to make what's called a terminal alkyne, but that's later on. Okay, so let me formally introduce you to this new reaction, the one in Unit 9. This is, we'll call this, well, Unit 9. We'll call it A reaction. I know I haven't been labeling reactions this way, in this manner, but well, let's try something new. So Unit A, or Unit 9A reaction, we're going to call this double elimination. Yes, it's the same elimination that you've learned about in the previous unit, Unit 8. So what do you need for an elimination? Well, we learned that if you have an alkyl halide, you could use a strong base. Well, this is a strong base, and we do have a dihalide. So we're going to do a double elimination to not get 1 pi bond, but to get 2 pi bonds. And I'm just going to use this example as our general reaction. BR. It could be dichloride. Oh man, I put a C. Fantastic. It could be dichloride or dibromide. It doesn't really matter. Okay, sorry about that. Okay, and the base we're going to use is NaNH2. And that is the preferred base. Could you use something like NaOH? You could, but we want to use a very strong base. Since we're doing a double elimination, we want to make sure that all the starter material gets eliminated. The BRs and the hydrogens get eliminated. Do you remember the elimination, though, what it's called formally? it's a beta hydrogen elimination. Hopefully you remember that, because for us to remove this bromine, we need a hydrogen in the beta position. But we have two beta positions, okay, and both of them have hydrogens. Okay. Let me draw out the final product, and as we go through the mechanism, I'm going to give you a couple of notes to help you understand why this happens, because it's actually not that obvious, because we have actually multiple beta hydrogens. Why couldn't we have made, two double bonds instead of one triple bond? You'll see what I mean in just a bit. Mechanism. When you have this dihalide, the bromines are on adjacent carbons. Put dots on the carbons that they are attached to. Okay. And I'm going to do that also with our product up here. Because before I go through the full mechanism, I want to put a little note here. If you can make an alkyne from the dihalide, if you can make an alkyne from the dihalide, do it. There will be some cases where you can't, and there will be some cases where you can do multiple things and not get the alkyne, but you should always strive for the alkyne. We're just going to attribute this to stability, because the other side products that you could get are not as stable, and I'll have time to go over that. So basically, if you can make the alkyne, do it. Because if you think about our first reaction here, plus, remember how you have to separate the counter ion, the cation sodium, from the anion NH2-. It seems like I have quote-unquote space between the two dots to put two pi bonds to make the triple bond. You know when we can't do this? We couldn't have done this if there were two methyl groups on this carbon, right? Because that carbon, if it has two methyl groups, you wouldn't be able to fit. That would be a carbon with 5 bonds. So that's what I mean by there are some cases where a dihalide, it is impossible to make an alkyne. Now if I think about this molecule here, let's say I want to get rid of this bromine on the left. So I arbitrarily chose that. That would mean that I would have to remove this hydrogen right here. Right? Isn't that the beta position for this bromine? So what you're thinking about is sequentially doing an elimination for these two bromines. But to remove this bromine, we have to remove a beta hydrogen. Now, why am I not removing this beta hydrogen? Well, stability-wise, a double bond in the middle is better than a double bond at the end because it's more substituted. Okay. And another thing is, again, we're just going to go with this rule. If you can make the alkyne, do it. Okay, enough talk. Let's get that. Oh, by the way, what kind of elimination is this? Is it E1 or E2? You have a strong base. You know that this is going to be an E2 mechanism. Look what we have here. This bromine still exists. Methyl. What exists on this carbon here? Right there. The one on the left. We still have a hydrogen there, which is perfect. Why is this perfect? Because now, to remove this bromine, I can remove this beta hydrogen. Okay. Now, I am kind of a stickler to draw all the products of the preceding step. Okay, so we did create NH3, and I'm going to draw NH2 minus over here. Okay. And we do our second elimination. Okay. I don't want to kind of clutter up the drawing by drawing a lot of alpha and betas. Actually, I might. Alpha, beta, beta. Because what I'm interested in is removing this first bromine, the one on the left. So I'll give that the alpha designation, and the betas are next to it. You notice that I remove the beta hydrogen that makes the more substituted double bond. Okay. Here, right, I could have taken off this beta hydrogen on the primary carbon, but again, I want to make the alkyne, so I'm going to remove the beta hydrogen on the left, not on the right. Okay. And you see what we get? We do get our triple bond like this, plus another NH3. Okay. All right. So this is the mechanism. This is man, messed it up. It's an internal alkyne. That's going to be important in just a bit. Internal alkyne. Now this takes practice, okay? Because, do you have this? If not, go ahead and pause it. This takes practice because, like I said, not all dihalides can be turned into an alkyne. Take a look at this one. My question is, can this be turned to alkyne? We know that we took a dihalide and made it into alkyne. What about this one? Cl and that. Okay, so that's a dihalide. The thing is, when you do our trick, okay, well, okay. I am going to, it doesn't matter which chlorine I remove first, but what if I remove this chlorine here on the right? If I use, again, NaNH2, now let's try this without drawing the mechanism. We're going to remove this chlorine, but we're doing that by removing this beta hydrogen on the left. And I have this. Okay. Now if you don't know how I got that, you have to draw the mechanism. Okay. For this first elimination. Oh. Whoa. Chlorine right here. Okay. So if I wanted to remove this chlorine right here, right? I am thinking that I am going to remove this beta hydrogen on the left, which is reasonable because we're making a tetra substituted alkene. Okay, I would rather do that than make the alkene on the right, because that would be mono substituted. But what do you notice about this chlorine right here? There's no beta hydrogen here. Okay, not only that, if I try to make a triple bond here, I would get something ridiculous. I would get a carbon with 5 bonds. So in this case, we're going to get kind of a weird molecule. With the second serving of NaNH2, we get this, and it's going to look very, very strange, because I'm going to remove the beta hydrogen on the left. And that will give me a double bond on the left, and it will look like this. We're going to have 2 hydrogens on the left now, because we remove one of them. And we have a double bond carbon. Okay, we remove this chlorine, and we have another double bond to this carbon that has 2 methyl groups. And I'll just use line structure for that. If you count the carbons, I think I'm good. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this carbon here has 2 methyl groups. This carbon here has 2 methyl groups. This is a molecule where it's kind of strange, where you have two double bonds in a row. This is called allyne. And it's not as stable as an alkyne. Okay? It's not as stable. Let's not worry about why. Just know that it's not as stable as an alkyne. Okay? Because if you think back to our original alkyl halide or dihalide, I could have, like at this moment right here, I could have removed the beta hydrogen on the right and made a double bond right here and have two double bonds in a row. But due to stability, this hydrogen is actually easier to remove to make the more stable triple bond in the middle. It's going to take some practice, okay? It's not that easy at first, especially if you're not drawing the mechanisms. If this is not easy to understand, then I would draw out the mechanisms. Okay. So there's one thing that is a little bit, well, a lot of this is tricky, but there's another twist. What if our alkyl halide look like this? Our dihalide, sorry. Our dihalide looks like this at the end. Okay. Can this be made into an alkyne? Definitely. Because if I put my two dots here, to remove this bromine, I remove a hydrogen off of here. And to remove this bromine, I remove the beta hydrogen off of here. And that will give us our two pi bonds between these two dots. Ultimately, NaNH2, ultimately we're going to get this molecule. We have 4 carbons. 1, 2, 3, and then 4, which I'm drawing in a linear fashion because it's triple bond like this. Okay. So that's our final product. There's a twist here. I actually have to put a second step, which is a proton transfer, H2O. What's the difference here? The difference here is that I do not have to do this H2O step because here I have an internal alkyne. Here I have a terminal alkyne, and I'm going to show you why I need the second step. Terminal alkyne again is a triple bond at the end of the molecule. Let me show you this and why this is necessary. Again, if you can make the triple bond, you will make the triple bond and you will not make the allyne. The only reason why we would make the allyne here is that it's impossible to make a triple bond because this carbon has it's tertiary, right? There is no hydrogen here to help remove this chlorine next to it, right? You would need a hydrogen here and a hydrogen here to remove these chlorines to make the triple bond between them two, between the two dots. Okay, let me draw the mechanism for this, and I'm going to explain why we're going to need this water step. It's a little bit subtle, and this is one of those videos where you do want to watch it a second or a third time. Now, in my mind, it doesn't matter which bromine you remove first. Okay, it doesn't matter. Let me draw my base, my strong base, and I'm going to remove. Does it really matter? Yeah, I'm just going to remove this hydrogen right here, one of these two hydrogens. By removing one of these two hydrogens, do you realize I'm removing this bromine here? Because this is your alpha position, and now this is your beta. And again, we're going to try to put the pi bonds in between the two dots. Okay? In between the two dots. Alright, so let's do this. Ooh. See, I almost freaked myself out because I said, well, I was about to kick out this bromine, but I'm kicking out this bromine because this hydrogen is beta to this bromine, not to this one. So this one collapses, and we get that. Does it matter? Let me see. Cis or trans? It doesn't really matter. You probably want to draw the more stable trans version though. Let me see if there's cis and trans here. Yes, because this bromine is still there. Okay. So this is still good because see on this carbon, right here and right here, we have a hydrogen. That hydrogen we need to help kick out this bromine, right? Because this hydrogen is beta to this bromine. Now we did have one hydrogen left over. You don't have to draw it, but I'll draw it just so we can keep track of it. Okay. Plus NH3. Alright, so let's do our second elimination. Remember, this is called double elimination. NH2 minus, what do we have to remove? We want to remove this bromine, so this is your alpha carbon. So where's the beta? The beta is right here. Remember, beta hydrogen elimination. Bang, bang, bang. Another E2. So we're doing a double E2, if you want to know about the mechanism. Now this is where it gets a little strange. So we do make a triple bond, and I'm going to draw it linearly like this. Okay. We do. Oh, actually, every time we do an elimination, we also kick out a bromine. I don't know if anyone caught that in the previous mechanism. I'll add it in just a bit. So here we did kick out a bromine or bromide, and also we made NH2 into NH3. Now this is your product. This is what I actually drew here. But there's a big problem. This hydrogen right here. This hydrogen is acidic. Well, not super acidic, right? But it's acidic enough for the base to rip off. This has a pKa equal to 25. Terminal alkynes pK of 25. The thing is, remember how I said that you got to assume that you have excess reagent? Well, we're going to assume that we have excess NH2 minus as well, the reagent. And the thing is, this is such a strong base that, great, it could do the eliminations, but now it could also do the deprotonation. And just be careful, it should start from the bond to the carbon. And we get this, unfortunately. It's unfortunate because we had the product, but now we don't. What do we have? We have a C minus, which is fine because you want to be sure. You want to use a very strong base, and you do want to use a slight excess to make sure that all of your dihalide is converted eventually to the alkyne. Okay, this should have it then. And by doing that, we're going to over basify it, I guess, and we're going to get the C minus. But we'll have 100% of this. All we have to do is add water. Okay, so let me just show you this. We did create NH3. The pKa of ammonia is 36. Why do you think that's important? You can't forget the things that we've learned in previous units. Those are your two acids. Equilibrium favors the weaker acid, so it is going to the right. Now we are getting 100% of this molecule here. When we have water, water is acidic enough to protonate back your alkyne anion. And we have this. And this is our final product. So the point here is that if you're going to make a terminal alkyne, terminal alkyne, use a second reaction water. Okay. And it is a 1-2 step. So you do the base, get to this alkyne anion, and then add water. You do not have to use this water trick for an internal alkyne, because why? You don't have an acidic proton with an internal alkyne. This is our first synthesis, for me, our first true synthesis, going from alkane to alkyne. Okay, but there's a lot of subtle points to this, and in my mind, all of it is important. Okay, so practice the mechanism and understand that if you make an internal alkyne, you don't need water, but for a terminal alkyne, you need water because at some point you'll have 100% of the anion because this hydrogen is acidic. We'll do more synthesis. This is just the tip of the iceberg, but this is a good start.